In this video, we talk about linear fractional transformations, also known as Mobius transformation. This is our overview slide, which we will spend about 5 minutes reviewing before we go through each topic in more detail and with more examples. We will start by reviewing the topics in our last two videos, the first one being linear transformations. Those are transformations of the form W equals T of Z, AZ plus B. And we were able to break this transformation down into two steps or two composite functions. The first one is we just looked at the multiplication A times Z, and we see if A is a complex number, when we multiply it by Z, a complex number, what A does is it will lengthen or contract our vector Z and then also do a rotation. But essentially, the shape of whatever figure we have that we transform will stay the same. It just might be rotated, it might be enlarged or shrank. And then this B portion of the transformation, the second step, we found was just a translation. So we move it over in the X direction or the Y direction. So for this linear transformation, the image of the transformation for a given region is geometrically similar to the pre-image. The second step, the second composite function, takes a complex number and then takes its complex conjugate. And this second step is a reflection across the real axis. So our transform is a combination of first inverting the unit circle and then reflecting across the real axis. So this transform, we also found, maps circles and lines into circles and lines. And what we will cover in this video are linear fractional transformations, which are transformations of this form. T of Z, where Z is a complex number, is equal to AZ plus B divided by CZ plus D. So you can see where this the name comes from. First of all, the numerator and denominator are both linear, and they're fractional because we have a fraction. So the other name for these transformations are Mobius transformation, which I often use. So here we have our linear transformation, and then what we will see is we can rewrite this into a composition of three smaller, simpler transformations. The first transformation, capital Z, takes our complex number, and that's equal to cz plus d. So this is a linear transformation. Our second transformation, capital W, takes our Z from the previous step and transforms it to 1 over Z. So this is a 1 over Z transformation. And finally, our W, which is our complex number, which is the mapping of T of Z, so it's equal to T of Z, is equal to T of W, where W is 1 over Z, where Z is given here. So it's equal to A over C plus BC minus AD over C times W. So this is our last step. We will see algebraically that this expression here is equivalent to our original T of Z, but writing it this way in these three steps allows us to see that this transformation is a linear transformation followed by a 1 over Z transformation, followed by, finally, this is a constant times a complex number, is another linear transformation, which allows us to conclude that the Mobius transformations transform circles and lines into circles and lines, just like our transform 1 over Z does. And we also have this note that W equals TZ equals 1 over Z, this case over here that we studied in our last video, is a special case of the Mobius transformation where A is equal to 0, B is equal to 1, C is equal to 1, and D is equal to 0. The next thing we do is we note that there is an inverse linear fractional, which we have a formula for here, but we don't really work with this much in this video. The next thing we do is we note there is always a linear fractional transformation that maps three distinct points, Z1, Z2, Z3, onto three specified distinct points in the W plane, W1, W2, W3, and we use our formulas, our linear transformations, to do an example. But we also have an implicit formula that lets us just do this conversion automatically or quickly. but we will also see examples of this. And now that we've covered our overview slide, we can go back to each topic in more detail and with more examples. We start by reviewing topics from two previous videos. The first topic is of linear transforms, where W is equal to A times Z, a complex number, plus B. And we can break this transform into two other transforms. In other words, it's composed of two transforms. The first is this multiplication, and the second is the addition of B. So first, we'll say Z prime then is equal to A times Z. And this, if we have this by this line here, if A is a complex number, is equal to A e to the I alpha, and Z also a complex number written in exponential notation as Z equals R e to the I theta, then when we multiply these two together to get W, we get W equals AZ, A times R e to the I alpha plus theta. So what we see is this multiplication. First, there's an expansion or contraction of the vector by a factor of a, this lowercase a. And then there's a rotation of our vector by the angle alpha. The second transformation is the addition of b. So if z over here is equal to x plus iy, and b is equal to b1 plus ib2, then when we add z to b, we're going to get x plus b1 plus I times y plus b2. So what we see is we've shifted the x-coordinate by b1 and the y-coordinate by b2, which is why we say that b, then, the addition of b, is a translation. And one thing to note, in both of these we might expand or contract or rotate or translate, but there's nothing that really deforms the shape. And so the image of the transformation of a given region is geometrically similar to the pre-image. Our next topic of review is the transformation T of z equals 1 over z. And much like we did for the linear transformation, where we broke this up into two smaller transformations, first the multiplication by a and then the addition by b, so we could analyze these separately, we're going to break up Tz equals 1 over z into two transformations that we compose to get T of z. In other words, there'll be two steps. The first is we take our complex number lowercase z and we divide it by the modulus of z squared, which is equal to z over z times z bar, or z complex conjugate. When we look at the magnitude of this capital Z, the result of the first transformation, what we saw is it equals 1 over the modulus or magnitude of our original complex number Z. Looking at examples, so at a point exterior to the circle, modulus Z is equal to 1. So something exterior, something like the point 2 plus 0i, that is certainly outside the unit circle. That's mapped to non-zero points interior to the circle. So when we take z of 2, that's going to be 1 over magnitude of 2. So that's 2 over 4, which is 1/2. And also just in this form, 1 over 2 plus 0i. So this is definitely interior to the circle to the unit circle here. Conversely, points interior to the circle, the unit circle, are mapped to points exterior to the circle. So here's a point interior, the 1/2 plus 0i. So putting it into our z function, we get 1/2 divided by 1/4, which is equal to 2, and certainly that is exterior to the unit circle. And any point on the circle, it's mapped to itself. This step was important to show that the magnitude of z was equal to 1 over the magnitude of z here. But you already do get the sense here without, I guess this is more intuition, whereas this gives you the definitive proof. But intuitively, you can see that this already inverts the unit circle, because if you have 1 over z and the magnitude of z is less than 1, then you're going to expect, so if magnitude of z is less than 1, then it's interior to the circle, and you're going to expect 1 divided by something less than 1 to be greater than 1, so it would be exterior to the circle. Also, if you have 1 over z and z is outside the unit circle, in other words, its magnitude is greater than 1 and exterior to the unit circle, then when you divide 1 by something greater than 1, you're going to get something interior to the circle, something less than 1. So its magnitude is less than 1 and inside the unit circle. And then the second step in our function composition of t of z is equal to w of this capital Z is equal to the complex conjugate. And it's easy to see that this is simply a reflection across the real axis. And then the other really important conclusion we have is this transform t of z equals 1 of z over z maps circles and lines into circles and lines. And in our last video, we did go over these particular results, but in the interest of time, we won't review them again here in this video, but you can go back and take a look. What we are going to focus on in this video is the linear functional transformation, also called the Mobius transformation, and it looks like this. T takes a complex number z and maps it into az plus b divided by cz plus d. And you can see it's linear. The linear part of this name comes from the fact that the numerator and the denominator are both linear, and then the fractional comes from the fact that we have this division. For continuity's sake, we'll define t at infinity equal to infinity if c equals 0, and t of infinity equal to ac if c is not 0. And finally, we define t of minus d over c equal to infinity if c is not 0. And much like we did for the linear transformation and the transformation 1 over z, we're going to break t of z into smaller transformations that when we compose them together give us t of z. But that will allow us to study the smaller transformations more effectively. I started by moving my notes on the linear fractional transformation up here so that I have more room to work. We are going to start over here by writing t of z equals w as azw plus bz plus cw plus d, and that'll allow us to do our decomposition. So just looking at this, our t of z, remember our original t of z over here, is equal to az plus b over cz plus d. So I've rewritten that here, and this is going to be equal to our w. So I can multiply this side here by w and bring this cd over here, which I have done in this step. I multiplied out the w, I subtracted the cz, I should have subtracted the d. So now I have something in the form of azw plus bz. My b is equal to negative c, cw, and my c is equal to b, and my d is equal to minus d. So it's in this form, but just notice that here we have capital A, B, C, and D because they're not necessarily these lowercase a, b, c, and d. But we do have this here is of this form. And now we're going to break up this transformation into 3 steps. So when we compose these 3 transformations, we get t of z that we have originally. So I'm just going to underline the original one. Our first step is capital Z is equal to cz plus d, and we see that this is a linear transformation, so we understand how that behaves. Then our next step is w is equal to 1 over this capital Z, and here this is a 1 over z transformation, so we know how that behaves. That's the inversion of the circle. And then last, we're going to have our final little w, which is equal to t of z, is equal to a divided by c plus bc minus ad over c times w. So here we have a constant, and here we have a constant times our vector. So this is also a linear transformation. So we've divided up this linear fractional transformation, or decomposed it into 3 functions, each of which we've already studied before: a linear transformation, a 1 over z transformation, and a linear transformation. And now, to convince myself that these 3 steps do in fact equal my original transformation that I have over here, my t of z equal az plus b over cz plus d, I perform the 3 steps. So I have z equals cz plus d, so I wrote that here. My capital Z equals cz plus d. Now w is equal to 1 over z. So w now is equal to 1 over cz plus d. And finally, w will be equal to ac plus bc minus ad over c times w. So w is equal to ac plus bc minus ad over c times my w, which is 1 over cz plus d. And from there, I just do some algebra, and you can see algebraically what I will get is az plus b over cz plus d. And so now that we have the three steps, a linear transformation, a 1 over z transformation, which is this inversion of the unit circle, and another linear transformation. So this decomposition shows that any Mobius transformation transforms circles and lines into circles and lines, just as we had before. Because remember, the linear transformation doesn't deform or change any region's shape. And then the 1 over z does the inversion, but we know this inversion transforms circles and lines into circles and lines. And then last we have another linear transformation. So that's not going to do anything to the shape except maybe make it larger or smaller. So this entire decomposition, these three steps, still transform circle and lines into circles and lines. And also we want to note that w equals tz equals 1 over z, this function that we studied in the last video, this mapping, is a special case of our linear fractional transformation where a is equal to 0, b is equal to 1, c is equal to 1, and d is equal to 0. Okay, so next we'll do some examples. Our first example is to find the Mobius transform that maps z1 equals -1, z2 equals 0, and z3 equals 1 onto w1 equals -1, wt equals 1, and w3 equals 1. And I rewrote this. I find this is easier to look at. So t of -1 is equal to minus I. That's this mapping here. Oops. Let me draw this. T of -1 maps to -I. Z of 0 goes to 1. So t of 0 goes to 1. And then finally we have z3 equals 1 gets mapped to I. So t of 1 is equal to I. So this form is a little strange, but this form is nicer when we use the implicit formula, which we will learn next. Now I'm going to use these pieces of information to figure out what a, b, c, and d are equal to. When I start with t of 0 equals 1, and I like to always start with a 0 if a 0 is there because it's so nice just to be able to plug in 0. So what I get is if if z is 0, then the az and the cz go away, and I'm only left with bd. So bd is equal to 1, which means that b is equal to d. So now I can rewrite my tz equal to az plus b, cz plus b. Next, I can plug in t of 1 is equal to I. And so if I let z equal 1, plug that into t, and this is my new t because I've already established that b equals d, I'm going to get a plus b and c plus b is equal to I. Again, I just let z equal to 1 in this equation. So multiplying both sides of the equation by c plus b, I get a plus b equals I times c plus b. Now looking at my t of -1, so this is as far as I can get now. So I'll need to look at my last piece of information. T of -1 is equal to -I. So I'm going to plug in z equals -1 into my equation here. And I get -a plus b, -c plus b is equal to -I. So multiplying both sides of the equation by -c plus b, I get -a plus b is equal to I times c minus b. Now I can use these two together just by adding the two equations together. I'm going to get 2b plus, what do I have? 2ic, and here my b terms cancel out. So from here I get 2b equals 2ic, so c equals ib, and this should be minus ib. Now I can plug this c into this equation, and I want to solve, I made a choice. You can decide what variable you want to solve in terms of, but I decided I wanted to solve everything in terms of b. So I have a plus b is equal to I. Now I plug in my minus ib for c plus b. And again, I want to solve for a in terms of b, so I get a equals ib. Since I have c in terms of b, I wanted a in terms of b, so that now I can plug into t of z. So I have a, which is equal to ib times z plus b, and then c, which is minus ib times z plus b. That's over here. And then I can simplify this algebraically until I get t of z is equal to I minus z and I plus z. And one thing to note, there is always a linear fractional transformation that maps three distinct points, z1, z2, z3, onto three specified distinct points, w1, w2, w3, respectively. Before we do more examples, I do want to mention there is an inverse linear fractional. That is, t inverse of w is equal to minus dw plus b divided by cw minus a. I have the calculation here to show that this is the correct inverse. That is, if I have tz equals az plus b over cz plus d, and that's equal to w, then my t inverse, if I'm proposing that's minus dw plus b over cw minus a, when I plug in this w here that I get from plugging in z into t, so I plug in my az plus b over cz plus d for w, so I have minus d, and then my w plus b, my c, and my w from over here, minus a, I can algebraically show afterwards I get back my original z. So in other words, this t and this t inverse are indeed inverses. Now we are going to go back to this point that we had on our last example, that there's always a linear fractional transformation that maps three distinct points, z1, z2, z3, onto three specified distinct points, w1, w2, w3, respectively. And that was the example we had where we said z1 maps onto w1, z2 here maps onto w2, and z3 maps to w3. And so I rewrote this here. And I rewrote this here that, well, I started with t of 0, which is z2, maps to 1, and that gave us b equals d. And then we have t of 1 maps to I, that was z3 maps to w3, and we got this equation. And then t of negative 1, that z1 maps to negative I. And then we solved for a, b, c, and d, and found that tz must equal to I minus z over I plus z. We are going to do one more example with the special case where we have infinity here. So we're going to find the Mobius transform that maps z1 equals 1, z2 equals 0, and z3 equals minus 1 onto w1 equals I, w2 equals infinity, and w3 equals 1. And as I mentioned, I often like to start with where my x term is equal to, my z term is equal to 0. So t of 0 here maps to infinity. So what that tells me over here, when z is 0, my a and c terms go away, and I get b over d is equal to infinity, which implies that d equals 0. So now my t of z has the form az plus b over cz, and again, d is 0. I can now use my next terms, my t of 1. Where's t of 1? That's z1. That gets mapped to I. So plugging 1 into here, I'm going to have a plus b over c equals I, which implies a plus b equals ic. Next, I'll use t equals minus 1, which is our z3, gets mapped to 1. So plugging that into here, this is minus 1, I'm going to get minus a plus b over minus c equals 1. And so this gives me minus a plus b equals c. When I solve these two equations, first I can add the two equations together, and I get 2b equals c times I minus 1. When I subtract these two, I get 2a, and these go away, and then I get c1 plus I. So here I can solve for a is going to be 1/2 c times 1 plus I. So I plug that in. A here, z plus, and then b is equal to c1 minus I divided by 2. So I have 1/2 c1 minus I. And then we said, so everything's in terms of c, and I have cz, and d is equal to 0. So this simplifies to 1 plus I times z plus I minus 1 over 2z. So this is my Mobius transformation that maps these three coordinates into these three coordinates. This problem here and the last one wasn't too difficult to do by plugging in and solving some algebra, but there is an implicit formula for the linear fractional transformation that maps z1, z2 onto w1, w2, w3 respectively. In particular, we have this equation here that tells us w minus w1 times w2 minus w3 over w minus w3 times w2 minus w1 will equal to z minus z1 times z2 minus z3 over z minus z3 times z2 minus z1. And if at any point, if any point equals infinity in this formula, we modify it by simply deleting the factors involving the variable equal to infinity. If we want to rework this example here that we have already worked, the Mobius transform that maps z1, z2, z3 into w1, w2, w3 using the implicit formula, we start with the implicit formula. Here we have w minus w1 times w2 minus w3 over w minus w3 times w2 minus w1 equals z minus z1 times z2 minus z3 over z minus z3 times z2 minus z1. So this is actually not that hard. Like the formula looks kind of intimidating, but it's not, because we have w minus w1, which is negative I, so we have w plus I, w2 minus w3, that's 1 minus I, w minus w3, so that's w minus I, and w2 minus w1, so that's 1 minus negative I, that's 1 plus I, and that will equal to z minus z1, and z1 is negative 1, so that's z plus 1, z2 minus z3, so that's 0 minus 1, z minus z3, again that's z minus 1, and z2 minus z1, that's 0 minus negative 1, which gives us 0 plus 1. And so far this is simpler. The rest is just algebra, so we can verify that we have the same answer as when we did the problem previously. We had this other example we previously worked where we mapped z1 equals 1, z2 equals 0, and z3 equals negative 1 onto w1 equals I, w2 equals infinity, and w3 equals 1. So we used the fact that t0 equals infinity to find that bd equals infinity, and we said d is equal to 0. So we got this form of the equation. We used t1 is equal to I, and t negative 1 is equal to 1, and eventually we came out with this equation for tz. So our linear fractional transformation was I plus 1z plus I minus 1 all over 2z. So now we'll redo this problem using our implicit formula. So w minus w1, so where's w? w1 is I, so w minus I. Then we have w2 minus w3, so w2 is infinity minus w3, which is infinity minus 1, over w minus w3, so we have w minus 1, and w2 minus w1, again infinity minus I over here. Now we do the other side of the equation, z minus z1, that'll be z minus 1, z2 minus z3, that's going to be 0 minus negative 1, z minus z3, so that's z minus negative 1, z plus 1, and then z2 minus z1, so 0 minus 1. And then we also use the instructions that, where is this? If any point equals infinity, we simply delete the factors involving the variable equal to infinity. So we're just going to delete this factor, the whole factor. It's not saying delete this term, this infinity. It says to delete the factor, so that's the thing we multiply by. So we're just deleting this all together, and we're going to get w minus I over w minus 1 equals z minus 1 over z plus 1 times minus 1. And the rest is algebra, and you can verify that you get the same answer as we did when we worked this problem previously. Before I go into our review, I do want to say that on my complex analysis playlist, after this video, the linear fractional transformations video, I have a video that I did not make, but I linked to, that illustrates the Mobius transformation, and it's a really impressive animation. I encourage you to watch it and look and see how the circles and lines map into circles and lines. See that inversion of the unit circle. That said, we're ready to review what we have covered. First, we reviewed linear transformations as well as the transformation t of z equals 1 over z. And then we covered the linear fractional transformation, or Mobius transformations, which is of the form t of a complex number is equal to az plus b over cz plus d. And you'll see the numerator and denominator are linear, hence the name linear over here, and they are fractions, hence the name fractional. We found that we could break this transformation down into three composite transformations. One that was linear, another that was a 1 over z transformation, and then a third that was linear, which means because this here maps circles and lines into circles and lines, and the linear transformations do not change the shape of regions, this linear fractional transformation, or the Mobius transformation, will map circles and lines into circles and lines, as we see here. We also talked about the inverse linear fractional, and we gave a formula for t inverse of w is equal to minus dw plus b over cw minus a. And then we also did these examples of this fact here. There is always a linear fractional transformation that maps three distinct points, z1, z2, z3, onto three specific distinct points, w1, w2, w3. And we did this transformation, or we found these linear fractional transformations first just by using our formula, the tz equals az plus b over cz plus b, as well as using this implicit formula written here, w minus w1 times w2 minus w3 over w minus w3, w2 minus w1 equals z minus z1, z2 minus z3 over z minus z3, z2 minus z1. So that's it for this video, and I do hope you get a chance to see the video that is not mine, but I did link to it in my complex analysis playlist, to the video about the simulation, the animation of the Mobius transformation. It's really quite extraordinary. Well, that's it for this video now. Thank you for watching.